think maybe we can start, and then people will gradually
Sure.
keep showing up.
That
Let,
sounds
let
good.
me let me maybe introduce you. Hi, Anurag. It's great to have you as a speaker in our Bugout community, and hello everyone who joined this talk. If this is your first Bugout talk, welcome to our community. We are very happy to have you. Please join our Slack. In general, we do our best to facilitate like supportive environment and help each other out. You know, if you have some technical challenges or if you need some advice and in general support of the community, this is kind of support we're trying to provide in our Slack channel, where our Bugout community is. And today our talk is about offline reinforcement learning and how to accelerate offline reinforcement learning. And our speaker is Anurag Ajay, who is a PhD student at MIT. And maybe Anurag, you will like deep more in like your research and what you are interested in, and we're looking forward to your talk today.
Yeah, thanks for the introduction. So basically, yeah, my work is related to reinforcement learning, but more likely, like finding priors in reinforcement learning. So by priors, I mean, what are some of the visual priors which can help us accelerate tasks, like new tasks in the future, or what are some action primitives uh, which will help us accelerate, like tasks which we will see in future. So I will talk more about, I'll delve more into the second aspect of my work in this talk. And, like as we will go, like we will see, like how, yeah, as we'll go, we'll see, like how the talk progresses. And at a high level, basically, I want to, build a robot which can explore the world on its own and basically learn new tasks and be able to adapt to, like changing situations. So that's a very high level like goal I have, and like in trying to achieve that goal, I employ reinforcement learning. And yeah, so I'll begin the talk. So talk is kind of like I timed it for like 30 minutes. So feel free to ask questions in between so that we can make it more interactive. So yeah, this is the work I'm going to present is offline primitive discovery for accelerating offline reinforcement learning. This is a work that I did last summer in collaboration with Google. So reinforcement learning has been successful in Game of Go, StarCraft, and robotic manipulation tasks. But all these requires, like continuous online interaction with environment for a long period of time. And this is impractical in certain situations. Now consider a Boston Dynamics robot, which is trying to learn a task through online interaction. Now, if it falls a lot, it would break. And if it falls, like it will require a group of humans to reset it to the original position. So like learning, like learning a task in the real world will be, will be very hard uh, through online interaction for this robot because it requires a lot of engineering and a lot of care. Similarly, consider a chatbot which could lose its users if it says something meaningless while trying to learn with online interaction. So in some situations, you need to be very careful with the actions you perform in the environment. But even in these settings, it's more practical to assume access to a large multimodal data set of past interaction. Now, this data set can come from either humans or a set of situation-specific hand-designed controllers. Then once we have these data sets, we can learn the policy offline and only execute the learned policy. Now, this whole framework is called offline reinforcement learning. So just to distinguish it from like online reinforcement learning, which is also we just call it reinforcement learning. The main difference is that we learn from a previously collected data set, and there is no online interaction in the process of learning. And the online interaction only happens once we have fully learned the policy. So is the setup like clear to like everyone? Basically, that's the high level setup. Uh, Then the first question to ask is why offline reinforcement learning? Why not behavioral cloning? Like by behavioral cloning, I mean, like you have expert trajectories and you try to imitate those expert trajectories. So why offline reinforcement learning? Now, the first thing is offline reinforcement learning makes use of reward labels. So it can take data collected from some other task, which might be related, but or like some exploratory behavior from like the past and use the reward labels to exploit that past data for our current task. So for example, consider robotica arm trying to manipulate like a certain object. As you can see in like the entire video, it's not trying to do a specific things. It's just like exploring the environment. But now if your job is to like just arrange like the block which it just picked up, in that case you just need a reward function, and you just need to label these data with the right reward function, and then you can exploit the data from a very different task or from an exploratory phase for your own task. So that's like the first benefit. The second benefit is that it can stitch trajectories together. It can basically the reason it's able to do is again because it has reward labels. So consider two trajectories, between 3 points A, B, and C. Now, offline reinforcement learning is able to find shortcuts in the data set, which was never seen in the, like in the data set itself, like A to C. So the reason it does that is because once it comes at the, in between A and C, it knows that it has to go to C, and that's where it will get high reward. So that's where it, that's why it's able to like that's why it's able to move to C. But let's say if you were doing behavioral cloning, in that case, with only 50% probability will you go to C, and with the other 50%, you will first go to B and then to C. And that's just because behavioral cloning tries to imitate and or takes an average of the trajectories for a certain situation. It doesn't like take reward into consideration. So overall, like this is like the motivation for using like offline reinforcement learning in general. Now, in this work, we'll talk about how to improve offline reinforcement learning by discovering primitives, which are inherently present in large multimodal dataset of past interactions. Now, by primitives, I mean temporally extended like recurring behavior as highlighted. Like this can mean motions in different directions, as you can see in the picture. Our main contribution is to basically theoretically and empirically show that learning an offline policy in space of these primitives leads to improved policy learning. Now, I'll first describe the intuition behind our method. Now, again, consider this data set. Basically, in this, what's happening is that there is a maze, and then this whole data set, an ant is trying to explore the entire maze. It's not trying to go to any particular point, it's just like trying to explore the maze. Now, let's let's even consider a cartoonish view of the data set. Now we can see that motion in different directions can again be perceived as different primitive skills. Now, optimizing in space of these primitives reduces the task horizon and also leads to compact action space, which in turn leads to better credit assignment. So let me try to break down what I mean. So now instead of like your action space being joint torques, which you need to apply to ant, it can be motions in different direction, like go left, go northwest, go northeast, things like that. And once you specify that, the robot will take multiple steps in that direction. So that technically is simplifying the task. Like now you're not taking one step, you're taking multiple steps at a time. So your overall your overall effective task horizon is reduced just because you are not like reasoning over each actions, but you are now reasoning over each skills or each primitive actions. So yeah, that's basically the benefit of like learning primitives, and since it leads to better credit assignment, it helps in reinforcement learning. So to learn these primitives, we first learn a primitive. I'll talk about these more in details, but we first extract a generative model of the data set. I'll talk about later how to do that. Now, once we have extracted this primitive policy, which means that if you're given Z, it will do a certain kinds of behavior. So value of Z could lead a value of Z could mean that the ant will move in certain direction. ANS, by ANS I mean it also takes the current state of the world into account, which means its joint angles and the obstacles around. And action is like the joint torques, like it will actually apply in the real world. So first we try to extract that. And now when we are given a task, which is a reward function, in this case, let's say the task is reaching a goal, you will get +1 for reaching the goal, 0 otherwise. Uh, we can learn a task policy in space of these primitives as opposed to in space of action space. As like I said, since like the space of primitive skills is like more compact, like we'll hope it for it to be more compact, it's much easier for it. It's much easier for you to do reinforcement learning in that space. So that's the overall high level view of like the method. Now I'll dive into details with respect to each components. So again, the first step is trying to extract a generative model from unlabeled and undirected data set. By data set in this case, I represent trajectories by tau. So we have a set of taus, and each trajectories is a set of like STAT for C time steps. So basically, to extract a generative model, we will use to achieve that we'll basically use an autoencoding loss with a regularization constraint. Now, one way to implement that is to use beta VAEs. So what I'm trying to do is I'm trying to take a trajectory, state action trajectory tau. I'm trying to pass it through a neural network, which is kind of trying to guess a Z, which is like the latent primitive skills. And basically, then it's trying to decode the action given the state and like the skill Z using the policy pi theta. So basically, using the encoding decoding framework, which is very similar to what conditional beta VAs do, like that's how we are trying to extract like the skills basically pi theta. So that's like the again beta VA is a well established like technique which people can like always look into. So once we have extracted the skills, by the way, feel free to ask any questions like if you have in between. Also, I don't see any questions like on my screen. So if you see any, just feel free to like let me know.
Yeah, sure. If I see, I will
Yeah,
definitely.
of course, yeah, of course.
Okay.
Yeah. So once we have now extracted pi theta, so all we need to do is okay. Once we have extracted pi theta, we need to use it for downstream task, which is like going to a specific location as we saw in that case. But even before we go there, let's think about it more. Now we have extracted a set of primitive skills, and now we are acting in the space of these primitives as opposed to the action space. But what if the data you learned on was bad? Then your primitives will be useless for the downstream task. So basically, like there is some chance that learning in space of these primitives will like incur some suboptimality. So first we want to characterize how that suboptimality will look like so that we know what downstream task we should use these primitives for. Like that's so to understand that. So basically, let's define the suboptimality. By suboptimality, I mean the difference between the pi star you will learn in the actual action space and and the policy you will learn in the primitive space. Now, okay, one thing you can always ask, okay, if we can always obtain an optimal policy in the action space, why do we even do primitive skills? So I think the question is the difference between existence and optimization. So yes, like a optimal policy will exist in the action space all the time, but it will be very hard to find that like policy. Like the optimization process, uh, to perform that optimization might be very hard due to the problems I laid out earlier, particularly being you have to you have to basically reason over like longer trajectories, or you have to like use like more complex action space. Now using the space of primitives allows us to shorten the task horizon, and it also basically allows us to like shorten the task horizon and also like make the action space more compact. So that's like the benefit, but there is also a downside which we'll not try to characterize. So the first thing is how much data is representative of pi star. So pi star is the optimal policy for a downstream task. And the second is the autoencoding loss, because if your optimization failed, that means like you will incur some suboptimality. So basically, just to formalize it more, we can assume that the data set comes from a mixture of policy or a distribution of policy, where we sample a policy pi, we sample an initial state, and then we execute it. So that's what we are assuming. That's how the policy is being generated. So basically, to basically characterize the difference between the data set and the behavior of the optimal policy for downstream task, we'll use like this particular measure. This is called total variational distance. So you can think of this as like basically distance. Like not if you don't want to get bogged down by math, intuitively think of it as the distance between the data and the behavior required by the optimal policy for the downstream task. And the auto encoding loss from like the equation in the last page, let's say that's epsilon c. We can say that again, like don't I'll explain like the equations, but basically like the suboptimality is characterized by this equation. So it means that if your autoencoding loss did not perform well, like, or it was high, that means the primitive learns weren't that the primitives learned weren't that good. So that means the suboptimality will have a higher upper bound. Or if your data set is not representative of like the downstream task, again the chi, like that will be high. So basically, like the suboptimality will be low only when your optimization worked, which it should, like it usually works out. And the downstream task should have some relationship to the data set. So basically, I'm trying to formally characterize what kind of downstream tasks our method will work on. And this is basically like a formal equation for that. So now again, going back to our, so basically the main takeaway from this slide is that you should be, once you have given the data set, once you have learned the primitive, you should be kind of careful about the downstream task you're going to use it for. That's like the high level takeaway from the slide. Now, once we have extracted the primitive skills, again going back to using it for like learning a task policy. So we have now extracted the primitive skills. Now we are given a labeled data set, which means we are given a reward. Like all I did was I took the unlabeled data set. I have a reward function, and I basically I labeled it with like the rewards basically. So now I can use the encoder to relabel, like I can use the encoder to basically relabel like these data with latents. So I get like two kinds of data set. One is the data set of higher level transitions, which means it considers all the C step transitions using which you will learn high level policy. And then it also labels the low level transitions with like the latent, with the skills present. Now, for learning the high level policy, you will use offline reinforcement learning, and you will use the data set like shown, which means you will be using C step transitions. And your task horizon will be reduced by a factor of C. And for that, we use the algorithm known as conservative Q learning. It's by Averill, like published in Europe's 2020. So you will use this method. So basically, I'll briefly like describe this method in one sentence, but basically, uh, all it does is that it minimizes the Bellman error as it should, and then it tries to ensure that the Q value for the actions which you haven't seen should not be too high. So basically, it's trying to of uh, minimize the Q values of the actions which are not in the data set, and maximize the Q values of action in the data set. The idea is to stay close to the things you have seen in the data set. Again, that's like basically you can basically think of this as an offline reinforcement learning method, which I use for learning task policy. And again, the task policy is learned in space of primitives. Now, then you can ask again, like how is learning in space, like in primitive space helping us as opposed to learning in action space. So well, also just to mention, we also kind of fine tune the lower level policy again with behavioral cloning. um, it just like helps us get a better performance. So again coming back to the equation, I'll try to describe what the equation means. Again, don't I'll explain the meaning. So basically, the two things to pay attention to are these two. So this suboptimality means how far the learned policy is from the optimal policy. So in this case, you can see the suboptimality decreases as we increase the length, as we basically reason over like longer trajectories or longer horizon primitives, and if the action space learned is like smaller. So basically, if I learn a compact action space and if I argue over like long time horizons, I will have less suboptimality. But we should be kind of careful with this argument. If we let's say if we learn a primitive space which is like too low, then the epsilon c, which is the autoencoding loss, will go high. So there you can only reduce actions, you can only compress the primitive space to a particular point. Below that, it will like harm you. Same goes for reasoning over long trajectories. You can reason over like longer trajectories, but if you make it too long, it's hard to like kind of reason. So, I mean, a good example to think in terms of like what's the appropriate thing to like reason. Think about this: if you're going to like like a different country, you do not plan each and every concrete steps of what you would do when you would land in the other country. You would first plan out how to get taxi, or like you would basically reason over like kind of short, not too short but not too long of like time horizon. So basically, that's what these equations formally show. Now, once you have learned these, once you have learned the task policy, you basically execute it, and the z, which is like the primitive skills, is sampled every c time steps, and then basically the once you sample a z, the primitive policy will execute it for the next C time steps. So basically, you can see like the task policy is acting at a slightly lower frequency. It's outputting Z once every C steps, and primitive policy is kind of acting every step. And since you're only learning task policy with offline reinforcement learning, it means that your task horizon is again kind of reduced by a factor of C. So this is the overview of the method. Now, the environments which I use in the paper are taken from like the data set, like D4RL environments. So the first two are like navigation environment, where you are given a data set of exploration, where like the ant is going exploring the maze as it's shown in the picture. It's just like exploring the maze, and then you will be given a final task, which is like starting from one end and reaching the diagonally opposite end. So that will be your task. And in the kitchen data set, and in the kitchen environment, the robot is basically exploring like how to manipulate objects in a kitchen, and then the final task will be like keeping objects in a particular configuration. These these again tasks are taken from like D4RL, and the data set was provided by that paper. We learn in the space of states and actions, basically joint angles, and like the action space is joint torques. But again, we uh, compress the action space to like more primitive space, which I talked about earlier. So these are the environments which I will be describing my methods on. And so for offline RL, you can see that if I combine a method of like offline reinforcement learning with conservative Q learning, we see like we see a huge increase in performance, and at least like in these environments. So we are able to specifically in like ant maze large, we are able to jump from like 15% to 70%. And I think the main reason the jump is coming is because like we are abstracting. We are not like trying to reason about each and every time step. We are abstracting away and like reasoning over skills, basically. Should we go in this direction or should we go in that direction, and so on. And on the kitchen data set, you can see that like we also like DN over SQL. There's a complete another method which EMAC, which was again like a concurrent work done. Like that doesn't do as well on ant maze, but that does like also improve in like the kitchen maze, in the kitchen environment, basically. So these are the results on offline reinforcement learning. uh, Qualitatively, you can see this is a heat map of like the how the policy of the conservative Q learning will look like. You can see in case of CQL, it's making wrong turns and kind of getting stuck in the corner. So it's not like really going towards. I mean, it's going sometimes, but it's not really going like too many times. It's also making wrong turns, and hence the accuracy is like more like 50%. In our case, it's again these are again heat maps. You can see that our method also is not 100% perfect. It does get stuck towards the end at times, but it more number of times, 80% of the times, it's able to reach the goal location. Same for like in case of large ant maze, you will see that in this case the CQL is getting stuck mostly around the initial points, and like our method is again able to like again with a 70% accuracy kind of get to the final location. Again, I don't have these visualizations for like kitchen, and that's just because that's a slightly harder environment to visualize. But overall, like you get like it's able to like in kitchen environment we get accuracy about 70 to 80% of the time. So this is like one set of tasks. Now the other thing you can ask is, okay, uh, I'll explain what I mean. So far, what I said was once I've learned a skill, once I've basically like learned a skill, I will give you a reward function and then you can use that reward function to solve a task. Well, that's one way to like indicate what task you want to do. The other way is to give some demos of the task. So this setting is called few shot imitation learning. So rather than providing you with a reward function, I will actually provide you with 10 demos, or like in our case 10 demos. You can provide it with 5 demos or how many depending on your environment, but like we provided with few demonstrations. So to adapt OPAL to that framework, all we need to do is we once we have learned the skills, we basically take the expert demos, again pass it through encoder, divide it into again like higher and lower level data set. And then like since we are just imitating the expert trajectories in this case, we don't even need to use offline reinforcement learning. We just like use behavioral cloning on high level data set as well as low level data set. So this is another way in which I can adapt my OPAL framework, like to few shot imitation learning framework. And to give you an example of what I mean by expert demos, like in context of like small like ant maze medium and ant maze large, it will be given 10 of these trajectories which I just showed in the video. which is basically like going from one location to the other location. And yeah, that will be the expert trajectories which the policy needs to imitate. And as you can see, like if you just do behavioral cloning in the expert trajectory, you do get somewhere. It's not like, at least on the medium, you do get, like, you do succeed 30% of the time. But like when you use opal, when you're imitating skills, when you're basically like imitating over the skills, it's much more robust. So you get an accuracy of like 80 and like 60%. And we also compare it to like a competing method, which is like the paper I mentioned. Again, just to be clear, the main focus of this work was offline reinforcement learning, but we are showing how we can adapt our method to different frameworks. And then again, like the last, last framework will be multitask reinforcement learning. So what do I mean? So let's again say we have a source task. So far we always have a source task. So we have a source task in which something, like agent is like exploring in certain ways. We extract, skills from it, as we have, so as I've shown how to do that. Now, rather than basically performing same task for different configuration, I can also perform a bunch of new tasks. So basically, like, these are the new tasks which I took from, like, there's a environment called meta world. That's where these tasks come from. So basically, once I've learned a primitive skills from a particular task, the question becomes, can I transfer to all these new tasks? So we can easily adapt the OPAL framework, which means once we have extracted the primitive policy, all we need to do is to basically learn a task, basically keep the primitive policy fixed, and learn a task policy on top of these primitive policy, using any standard, off the shelf reinforcement learning algorithm. And then we can show that, if we basically try to learn these multiple tasks over, over like primitive skills extracted from a different task, we can gain a lot of like improvements. For example, we were able to, like, gain clear improvements over PPO. And like you can see, like, we're all already better than, like, soft actor critic. Again, like, you can, like, again, there are other approaches which have been studied in context of, like, multitask transfer, which you can also use, but those are orthogonal approaches. In this case, all we are arguing is that if you want to transfer to a new task, but if you have demos from a set of related tasks, in this case pick and place, you can just use that task to learn some skills, and then basically do reinforcement learning in the space of learned skills. So that's like so this basically again like shows us how to adapt, multitask transfer to with our framework. So yeah, these are the three frameworks I have with Opal, and like this is basically what I wanted to, like, present in the talk. Basically, give us simple. I mean, I hope it's like a kind of a simple method to extract primitives, use it for offline reinforcement learning, show how it benefits offline reinforcement learning, and at the same time show it can adapt to, like, few shot imitation and also like multi-task transfer. So that's all I have for the day. And I specifically left, like, some time for people to ask me questions, or, like, you can also ask me general questions about what are the other context in which, these primitives can help you, or like, will learning primitives be useful for your own problem setting, and that problem might not necessarily have to be something related to robotics. So yeah, that's all I have for today, and I'm happy to take any questions.
Mm. Thanks, Anurag, a lot. Guys, if you have questions, feel free to post them or unmute yourself and ask directly. Actually, you somewhat responded to a question I had, because I remember, like, a couple of years ago, PPO algorithm was so popular, and in reinforcement learning research, and I wondering how it's compared to PPO. Is it like sort of PPO still dominant in research, or is sort of gradually other policies
Yeah.
nowhere?
So yeah, let me try to answer that question in, like, multiple. So in our case, we are, like, in this case, as you can see, we are actually using PPO, which is so in our case, we are agnostic to the reinforcement learning algorithm which is being used. So all we are doing is we are learning a primitive space, and then you can perform PPO on the primitive space. Now, when it comes now, with regards to what is, like, how well it does, like, or what's the current state of the RL algorithms, it's like PPO is useful, but the problem with PPO is that it's on policy, which means you can only use the data which you have recently sampled. You cannot use the data from the past. So for using the data from the past, you need an off policy algorithm, and that's why you will see algorithms such as soft actor critic or TD3 to, like uh, TD3 in like practice. And but those are still off policy, which means you need offline online interaction. Now for offline reinforcement learning, like again, there has been like again like a more recent resurgence, and that's where we can use conservative Q learning algorithm for that, which means that you have a previous data set and you don't even act online and you just learn based on that. With regards to, let's say if you're working on a research problem, I would actually suggest you, let's say if you're working on games, the advantage of PPU is that it's very easy to get it to work. Like it might not give you the best performance, but it will give you a decent performance, and it's easier to get it to work. So it will give you an idea of how hard the task is, assuming you're using a simulator. Now if you need to be sample efficient, that's when you might need to use other, soft actor critic. Now if you don't even want to act in the real world, just use the previous data. That's when you need to use conservative Q learning. And in all these three cases, like if you want to reason over like skills as opposed to action space and make the problem easier, you can always use like OPAL or like other methods for extracting skills. So that's like the landscape. Like,
Mm-hmm. I see a question from Eric. Can you provide more examples of tasks versus primitives?
Okay, so another, I think I can like try to go back. A good So okay, at least in Ant, it's very clear. Like Ant, like it's the simplest example. That's why I, like to get the point across, it's kind of like that's why I use that as an example. Now let's look at the kitchen video. Like in kitchen video, the task could be arranging all four objects as it's shown in the video in a particular at a particular pose. Now individual skills or individual primitives opening can actually be reaching some object, reaching for some object, or opening something else, opening or like sliding something, and then you can combine these primitives to basically like construct a task. So uh, that would be my answer. Now like not to get too abstract, but you can say that okay, primitive again like another way to think of primitive as it's like simpler tasks which you can learn. But those simpler tasks are but those simpler tasks always reoccur in like different fashion. So whenever you're given a hard task, you often break it into simpler tasks and you learn how to do the simpler task using primitives. So that's like the like the connection between the primitives and like the tasks.
Yeah, I wanted to kind of follow up on that actually.
Uh-huh.
So I think it's kind of a question about the level of abstraction.
Yeah.
So obviously you can inject prior knowledge about the level of abstraction, but let's say that we don't want to do that. What's your thought for sort of finding the most appropriate level of abstraction at which to break things into primitives?
Yeah, that's a very good question. So in our case, we actually did not assume the level of abstraction, but we did assume like there's a particular hyperparameter. I'm again going back to this diagram. The level of abstraction in our case is basically decided by the hyperparameter C. So in our case, basically the C means like the time period for which a primitive would execute given a particular Z. So to decide on the appropriate level of abstraction, I think that's kind of like in my intuition is that like let's say if you have a task, first you try to study the task or study the data set coming from the task. You see how many time step it might take your agent to reach a particular object or like to reach or to do something meaningful, and you can have that level of abstraction. Now let's say you're easily able to learn that. Then you can maybe try to reach furthermore. Let's say you can try to see if you can learn even more kind of like primitives, or like you can learn better abstraction by like planning, by basically learning how to do longer horizon things. But so I think it's more of I know it's not a great answer.
I mean, well, something that like something occurs to me, maybe this is the wrong direction, but like this was just a thought. So for instance, trying to find a level of abstraction where the primitives reoccur, the highest level of abstraction where the primitives reoccur frequently.
That I agree with. So that's a very nice encapsulation of what I wanted to say, but you put it in a nicer manner. Yes, like that I agree with. So that's the high level principle. Now how you get to that, that's where it kind of becomes, in terms of optimization, slightly harder. So that's why, like in our case, like the way we made it slightly easier is by choosing a hyperparameter C, and then basically C is decided by looking at the data. So what you're suggesting, we are actually doing that by actually looking at the data and injecting a prior C, and then like doing the variational inference or like variational autoencoding. Another way, I think, like there's a group of work literature which you can also look. It's called options learning. So option learning, they also like try to extract the number of timestamp or the number of like timestamp a skill would want to act on. So they also like try to decide the length. But like the issue there is that it's very hard to optimize. So that's what I tried earlier. Like I also like tried to find the right level of abstraction. It was kind of I was either running into the issue of like it was kind of learning one level of abstraction for some reason. Like the optimization basically was like it was getting stuck in local minima, and hence we like decided on like to do this. But yeah, like conceptually, like option learning would be like the field I would look into if I were to automatically learn how to choose the right level of abstraction.
Yeah, I think Niraj has a good point. You should I say it?
Go ahead.
Niraj, go ahead. Hello, sorry, I can't
hear you well.
Hear you. Yeah.
Yeah, it's something.
I cannot hear for some reason.
No, but we can't hear you well.
No, can't hear you. Can't hear you.
He's muted, so I think.
No, oh, now you're muted.
You mute yourself. Can you unmute and try again?
Nope. Even unmuted can't hear it. Can't hear him.
Yeah.
He says a minute.
How is this? Is it?
Yeah.
Yes. Yes.
Yeah.
Great.
For some reason, it selected microphones. Microphone that.
Yeah, that happens.
Yeah. Okay. So basically, my question is this: if you treated your data as like say you have like several different candidates for like what the primitive should be, you could treat your data as a sample from a probability distribution over primitives, and then you could just choose like the set of primitives for which that probability distribution had the highest entropy, like the highest information theoretic entropy. How would that compare to what you guys are doing?
I think that's like, so from what you're saying, that would basically kind of, that would be related to the option framework I said. So a more recent instantiation of that work would be, I think it's called temporal variational inference. I'm not sure about the title, but the authors are Abhinav Gupta and Tanmay Shankar. So those are the, so basically, like I think in that case, you will run into the two issues. Like, so we did try that approach. So you will run into one of the two issues. Either the primitives getting learned would like, you will learn a one-step primitive, because at times like it's very easy to, get to a okayish level of performance with one primitive, because that's just the action space. Or the agent, or if the task is too simple, like the agent will try to learn the entire task. And that's where like it will get stuck into. So how do those papers like get across, like basically like try to avoid those points? They try to have like certain regularization. They say that, okay, you cannot like literally, if you basically have one step, basically if you have, one step primitives, you get penalized. So if you do like, if you have those kind of things, basically like you will end up with primitives of like different lengths. The thing is that like I think the difference comes between that's harder to get it to work in practice, and this is maybe a slightly suboptimal thing to do, but it's like much easier to like get it to work. I think that's where the difference comes in.
I see, because the highest entropy distribution would be over the actual action space like that's available to your agent in the right. Okay,
that's why you need like certain regularization to
yeah. Okay, so you have to say that like each primitive needs to be at least this complex or something like that, and then that's a parameter. Yeah. Okay.
Yeah, basically.
Okay. By the way, I joined a little bit late. What are the primitives that you would learn for ant maze?
Yeah, in ant maze, I think I have a like, first I can show you a more cartoonish way, and then I can basically like think about this. Like it will be something related to moving in different direction. Now, obviously, since you're in a maze, the things you will be learning will be like, okay, how to go around like an obstacle, or how to just like go move in free space. So it will be a certain combination of those, but this is more of a cartoonish representation of that. So yeah, that's the primitive you will like.
Have you guys considered trying with Tetris? I would be curious to see like what Tetris primitives were or something.
That's, yeah, we did not try with Tetris. We just like, I think what so just to clarify the process, I think we already had the data set from like the D4RL, so we just like stuck because we had a data set and we had a set of environments, so we just like stuck to that. But I think Tetris would also work because Tetris also has that idea of like given like okay, given certain things are falling, how do you form like
Yeah.
a particular kind of structure which can be combined into a larger structure. So I think it's a good problem setting. Like
Actually, there's a lot of videos of professional Tetris matches on YouTube. I discovered this like procrastinating one day, and there's like hours and hours and hours of videos of people playing professional Tetris matches, and they definitely look for patterns. Like they try to build certain patterns so that when like certain blocks come through, they can kill like many rows at the same time. It would be really cool to see like what your agent.
Yeah, no, that's a very interesting direction to follow. Yeah, no, that I agree with. Like yeah, I mean like Tetris is good, and then I think there are many other real world examples. Like for example, another good thing which comes to my mind, which is good to try, is like tool use. Basically, if you're using any kind of tool, like how do you like pick up a hammer, and if you know how to like basically like hammer a nail, like how can you use it for more complex tasks? So yeah, there are like good examples of using primitives.
Mhm. Also, Rubik's Cube is another one because people who
Yes.
solve Rubik's Cubes, they try to reduce it to a known state and then they have
That is
yeah.
that is true. Yes, that's yeah.
So just to clarify, basically, like offline reinforcement learning is basically if once agent was trained on some environment, you guys collect that data that already generated and then sort of like reuse it.
Yes. So basically, let's. I think maybe the best picture. I'm just like trying to find a better picture to highlight. Is just give me 1 minute. Yeah. Let's think of this. And this is a good environment to highlight. Let's say if you want to just open the drawer, if that is your task, but in the past someone has basically tried to just explore the environment, then what offline reinforcement learning says that if you already have a data set of interactions, can you just like use it without even acting because the data set is already there. So that's what the issue is. Basically, if you have the data set, you just learn the policy using the data set alone, no interaction that leads to certain issues. And then basically, like you execute the learned policy online. And the idea is that obviously you can always fine tune the learned policy when you're executing it offline. But the idea is that that prevents you from doing something really catastrophic or like something really suboptimal in the real world. So that's like, but let's say if you were in a situation where uh, acting in the real world doesn't have too much of a cost, there are problems such as that, then maybe I would stick to offline reinforcement learning, just because if you can basically execute a lot in simulator, I think then it's like it then like yeah, you can use the data set from past interaction, but if that data set is not there, you might as well use online reinforcement learning. So I remember there was an example from DeepMind where they used something to optimize their electricity condition. I'm kind of like blanking out on the exact project, but it was I think few years back. So that's one example where online reinforcement learning might be like fine because they already had a well designed simulator which they can use to learn a policy to execute in the real world.
Mm-hmm. Do we have other questions? If not,
I'm kind of curious, there's a lot of work in dynamical systems, like in mathematical research on dynamical systems about
Yeah.
like symbolizing dynamical systems, which seems like quite similar to what you guys are doing as well, right? You're trying to find like some sort of efficient, like symbolic representation of like of what like an agent can do in like a continuous action space.
That is true. Yeah. So yeah, that is true. So basically, like just to give a brief overview, I think there's a related subfield called task and motion planning. So in those cases, people design symbols like they take like like they have like very specific symbols, which if properly designed and if you're executing it in a proper setting, you can actually get really cool robotic behaviors out of it. The hard issue become like if you're using like symbolic AI for that, the hard issue is how do you ground that to perception? That's where the challenge comes in. Like let's say you have a symbol, but now the agent is seeing is an image. How like the grounding problem, which is take that image and initialize your symbol with like the image, that becomes a harder problem. So there are people also like trying to come from that direction on how to solving the grounding problem. But yeah, there are many like you're right, like there are related fields which tries to learn symbols and like then do planning on top of the symbols.
Thanks.
Cool. I just shared again our link to Slack. Yeah, but we'll share your presentation, Anurag, and this the video recording. Yeah.
I'll also post my slides on the Slack link, so that works.
Yeah, cool, awesome. Thanks everyone for joining this meetup, and thanks Anurag for your time. It was really insightful to learn about this direction. Actually, I noticed many like research groups started like working towards offline reinforcement learning, sort of like very hot trend right now, right, in research.
Yeah, I mean, that's true. I think the reason is again because I think there was a push by Google and Berkeley. So they literally had like a bunch of 20, 30 papers over just like one conference cycle. So that since they have like a lot of like research power, they can, like, so that's where like it all started from. And that's because Google has recommendation system. So it totally makes sense for, using offline RL like at that point.
Good to know. Okay, thanks. Thanks a lot. And thanks everyone for joining this talk. Bye-bye.
But I think Jeff had a question.
Oh, Jeff, go ahead.
Well, I since we're ending, but I did kind of want to throw this in here, which is so it's still kind of banging on the same drum about sort of level of abstraction, but also about compositionality.
Mm-hmm.
So it would be possible to find a way of searching for the highest level of abstraction where a certain minimum number of occurrences took place, and where as an additional constraint, perhaps that there was some kind of compositionality constraint. So in other words, where the primitives could be combined in a minimum number of permutations, for instance, as something like that.
Mm-hmm. I think in our case, I think it's, so I can like try to clarify, like, in our case, basically compositionality might be coming from, it's not really compositionality, but like it's more, since we are using abstracted like skills, and since we are trying to combine, like execute one skill after the another, that's where the compositionality might be coming from. But I think your question is more like, it could be more about combinatorial generalization, which is that if you like, how do I generalize to a new combination of like an object, like we have seen some different combination of the past objects or something like that.
Yeah, or where it's possible. So in other words, some kind of constraint where the primitive could be combined with another primitive that it wasn't combined with before. Some kind of constraint that factors that in.
Oh, I see. Like maybe then in that case, you're talking about something like if you have Z1 plus Z2, like if I enter in a primitive policy, that basically leads to me doing some kind of a joint behavior, like, like trying to somehow, I don't know how to exactly describe that, but like,
or like maybe I can clarify. So let's say you identified primitives A, B, C, D, E.
Yeah.
But it turns out that in your data set, your primitive A, your primitive B only ever comes after A, and there's just no variation. And maybe there's some other thing that you can figure out where actually it wouldn't be possible for B to come after anything but A.
Yeah.
That's kind of what I was getting at. I think it's going to take some more work to get there, but yeah.
Yeah. I'll just like quickly like answer like that. Oh, so that's a very good. So you're saying that in data set, if A always comes after B, then how do you distinguish that? Because technically like the data set can see it as like a single skill. Yeah. So that's a point where I think our work doesn't explicitly address that. I think we might get around that issue by use of the hyperparameter C, but there is no conceptual thing which our work addresses. So that's a good thing to think about. Then maybe the idea is to, again, this is a very high level idea. I haven't done that, but maybe then the future task should inform let's say you get a downstream task, somehow that should inform a new set of primitives. Because like if in all the tasks B has to come after A, then it doesn't make sense for it to be two separate primitive. But if you can show me some example of task in which that's the case, So maybe there should be some, back and forth between, like primitive and downstream. I'm not exactly sure how to go about this.
Or like another way would be to do it from physical constraints. Like, so for instance, the robot actually physically would be incapable of going from primitive A to primitive D or whatever,
That's, yeah. I see. Yeah, I'll have to give some thoughts to that, but that's a good point that, like you made. So
Okay. Anyway, I'll stop asking questions.
no,
So.
I'm like, I actually have time, so I'm enjoying the discussion. It's just that I don't have I wish I can answer. It's just that I don't have a clear answer,
Yeah,
for-
I'm really more, I'm throwing out research directions.
Yeah. So I think in that, I think, but like, okay, my counter question will be that, like, I'm just like thinking out loudly. So sure, if there are no physical constraints, like that should not be in the data set, right? Because, or you might be suggesting that in data set it might be possible, but in the current environment setting, it might not be like possible just because there is some physical constraint. So you have to executing, so you have to executing that. Yeah, I think then in that case, I think like in that case, then you should have like a certain primitive which basically asks you to stop executing the current primitive in between. Not so basically like the action space becomes set of primitives, and if you're getting a wrong feedback in middle of some primitive, then you can try to send a signal to the down policy to stop executing and sample a new Z from that point. So that could be like,
something like that. Yeah.
that could be like one way to go about like the thing you said. Like that could be. I can see like how
But
to.
now you're not offline anymore, right? Now you're like sort of online as well. Like if you can
Yeah,
read,
that has to happen on. Yeah, so I think that's fine. I think like the whole point of offline is to come up with a reasonable behavior. So I'm assuming the reasonable behavior is already there.
But maybe what I understood. I mean, Jeff Jeff explained very well. But what I understood, like what I was thinking about when he was saying it was, what if you just like generalizability is an important notion, right? Like what if you just train, you can actually identify the right set of primitives by training on like partitioning the data in several different ways, and then seeing which set of primitives sort of survives generalization or like survives generalization
Oh,
like the most
I see.
number of like.
Okay, that's huh. I see. Okay. That's so basically you're saying that okay, maybe use a validation environment for eliminating like bad primitives, because like the validation environment will give you like some idea of, oh that's I
Have
think
a lot of data available, like you can still do it offline, but you can
Like making seeds and see which seed will survive.
yeah.
yeah, I think it's like now I kind of like more understand. Okay, so basically like you're saying that okay, like there are many level of abstraction which can be abstracted. Like they could be from perspective of the data, they could be equally good solution, but now you can use validation environment to eliminate like different so yeah, that's an interesting, that's
I
that's
don't know if that reflects what Jeff was saying, but at least I understood from that.
It expands on it. Yeah, no, and I think that's a very valid direction.
I think I also kind of got what Jeff was saying. Basically, like, what if, like, like two primitives in a data set come one after the another, or then how do you even distinguish like between like those things? But even like, for example, in data set, let's say if you always, like take something out of the cupboard and then you basically switch on the light, like those are in the data set, those will always be executed, but in the real world those do not have to be executed one after the another. So how do you I think there needs to be some form of feedback which tells you that a better separation is needed, which can be either in the form of validation environment or some feedback. But I think in that case you would, I think like optimization alone won't solve the issue. You need some more feedback in some way, because something needs to tell you that okay, this is not the correct thing. You need to like divide it furthermore. So that's like what my intuition is. I'm not 100%. Yeah, that's yeah.
I see Marco ask a question. What is your opinion on the micro psi? I don't know, what is it? Micro psi, which also uses imitation for learning.
I don't know. Micro. Yeah, I'm not 100. Micro psi. I think I would need to look into that. I'm not sure. But again, just to be very clear, there are also like again like concurrent works which might be doing something similar. But yeah, I'm not aware about like the micro psi paper.
Yeah, I I also never heard of it. Marco, maybe you can elaborate if you want. It's from Josh.
That's yeah. I'm just going to open the.
Mhm. Actually,
Yeah, I think I would. It will take more time. It's because I don't know about the work, so it might just take me more time. But yeah, like
we can come back to it later. Actually, I'm curious about one thing. I don't know. Maybe you covered it. Let's say if one task in one data set and another task in like completely different data set. So are you stitching together different data sets to sort of build up like one task?
I mean, again, in our case, we did not do that explicitly, but there is nothing in the, as long as the tasks are kind of related, like you can always like do that. So in our case, what we were doing is we were taking a one environment in which you were exploring one environment as much as possible, and then you were doing a particular task in that environment. I think towards the end, like the multitask transfer, we got to that phase where we were, doing what you are suggesting, which is taking from data set, but in that case we were only taking data set from one task and basically combining it with other tasks. Yeah, but I think like to your point, solving it for the task, to your point, I would say I think you can do that as long as the task is related. For example, in the last example case, if you have data set from all the tasks, you might not even have to do online transfer. You can just like learn everything offline. So I think you can do that. I think that's actually, to be fair, that's what actually many people at like Google like do, because the whole point is that if you have a big data set and they have lots of compute, you want to act as less possible in the real world, because that leads to to avoid the issue of safety and other things.
Yeah. You want reuse this offline data sets that
that's basically that's the I think that's what also happens in computer vision. Basically, you have large label data sets and now you want to like use those data sets. So I think that's like the equivalent, like what they were trying to achieve in like RL.
Mm-hmm. Cool. Thanks, Anurag.
Thank you.
Thanks, Jeff, Neeraj, and Marco, and everyone, Eric, everyone who joined this call today. Bye-bye.